Welcome to The Explainer. We're diving straight into the literal lifeblood of the modern AI boom today. Usually, when we talk about AI, we obsess over the massive processors, the GPUs, doing all the heavy lifting, right? Well, today we are focusing on the unsung hero that actually makes all that computation possible. Let's pull back the curtain and look at the hardware truly powering this revolution.
Think about this for a second. What if an AI chip's biggest limitation isn't the processor at all? Imagine you've got the absolute fastest compute engine in the world. It is a marvel of engineering. But the fuel line feeding data into that beast, it's the size of a tiny plastic straw. Obviously, it doesn't matter how fast that engine can run if it's literally starving for fuel. And honestly, that is exactly the situation we're facing right now with modern AI accelerators. As large language models have exploded in size recently, the compute engine has scaled up way faster than the memory fuel line.
So here's our roadmap for today. We're going to look at the AI memory bottleneck, HBM and stacking techniques, advanced packaging and CoWoS, some real-world HBM4 examples, and finally, the massive challenges, HBM4E and what comes beyond. Basically, we're taking apart the engine of an AI chip to see how it ticks.
All right, Section 1, the AI memory bottleneck. Let's figure out why these wildly powerful chips are suddenly hitting a brick wall.
In a traditional setup with normal DRAM architecture, memory chips are sitting way out there on the motherboard. They talk to the processor through these relatively narrow external connections. It's kind of like suburban sprawl, you know? Everything is spread out, and the commute just takes way too long. High bandwidth memory, or HBM architecture, completely flips the script. Instead of that sprawl, HBM places the memory intimately close to the compute system, and the interface, it is ridiculously wide. The upcoming HBM4 uses a massive 2048-pin interface. If standard memory is a 2-lane country road, HBM4 is literally a 2048-lane superhighway. It is a total paradigm shift. We're talking about moving data in massive parallel waves.
Here's the bottom line. Your compute power, your TOPS or FLOPS, is completely at the mercy of your memory bandwidth. An AI accelerator is churning through massive amounts of matrix operations, neural network parameters, activations, weights, the whole shebang. All that data has to constantly travel between the memory and the compute engine. If your compute engine is lightning fast, but your memory is dragging its feet, the whole system becomes severely bandwidth limited. You're not processing, you're just waiting. And the cost of that waiting? It's astronomical. Modern AI clusters cost hundreds of millions of dollars to build and run. Having those incredibly expensive GPUs just sitting there idle, twiddling their thumbs waiting for data, that is a massive waste of energy, time, and serious capital.
This brings us right to Section 2, HBM and stacking techniques. We're zooming in from that macro bottleneck to the mind-bending microengineering that actually makes this high bandwidth possible.
Remember that suburban sprawl analogy? Well, HBM fixes that by building vertical skyscrapers instead. Instead of laying memory chips flat, engineers are stacking them straight up. But how on earth do those top layers talk to the system down below? Enter TSVs, or through-silicon vias. These are vertical electrical connections passing entirely through the silicon dies. Think of them as ultra-high-speed internal elevators shooting signals and power up and down the building. Executing this is just wild. Manufacturers are literally drilling microscopic holes directly through highly fragile silicon wafers and then perfectly filling those tiny holes with copper to create continuous vertical pathways. The precision here is absolutely staggering.
Using those microscopic TSV elevators, manufacturers are now layering 12 to 16 individual DRAM dies vertically using 3D stacking. But there is a secret weapon at the very foundation of this skyscraper, a cutting-edge logic base die. Historically, memory was just dumb storage, right? It just held data until the central processor asked for it. Not anymore. Modern HBM4 designs, like the ones from Samsung, integrate a highly advanced 4nm logic die right at the bottom of the memory stack. This means the memory stack itself is now smart. It can actually handle vital data management and processing tasks on its own, which lets it communicate way more efficiently with the GPU. This is a profound shift in semiconductor design. Memory and logic aren't separate domains anymore. They are fundamentally optimized together in one single stack.
Moving right along to Section 3, advanced packaging and CoWoS. Because honestly, having a brilliant memory skyscraper is completely useless if you don't have a way to connect it efficiently to the brain of the operation, the GPU.
To make that critical connection, we rely on advanced packaging. And the reigning champion here is TSMC's CoWoS, which stands for Chip on Wafer on Substrate. CoWoS is a 2.5D advanced packaging technology. If you're wondering what that jargon means,
Well, 2D is just chips laid flat on a normal motherboard. 3D is stacked directly on top of each other, like our memory skyscraper. 2.5D is the magic right in the middle. It's placing the processor and the memory stack incredibly close, side by side, on a highly specialized silicon interposer. CoWoS acts as the foundational superhighway, tightly binding the compute brain and the memory bank for extreme AI workloads.
Picture the exact physical flow for a second. Right in the center, you have your GPU or AI accelerator. Sitting immediately next to it are your towering HBM stacks. Beneath both of them is the silicon interposer. Now, why use an interposer? Because a standard circuit board just cannot physically handle the microscopic density of the thousands of tiny wires required to connect the GPU to that massive 2048-pin memory interface. The dense silicon interposer bridges that gap. Finally, all of this sits on a broader packaged substrate to connect to the outside world. You aren't just plugging memory sticks into motherboards anymore. The package itself has become a heavily engineered, utterly crucial part of the overall system architecture.
Let's zoom back out to reality for Section 4, Real-World HBM4 Examples. Let's see these staggering engineering techniques applied to actual hardware rolling out in 2026. 3.3 terabytes per second. Just let that number sink in. That is the staggering bandwidth provided by a single stack of Samsung's commercially shipped HBM4. It's kind of tough for the human brain to comprehend data moving that fast, so think about it like this. 3.3 terabytes per second is roughly equivalent to downloading 1,000 high-definition movies in one single second. And that's just from one tiny memory stack. This is the absolute bleeding edge of hardware capability, engineered specifically so that your GPU is never, ever sitting idle. Looking at the sheer scale of the 2026 HBM4 rollout, you really see two slightly different but equally incredible approaches. On one side, you have Samsung, who pushed commercial volume in February 2026 with an extreme focus on speed. They implemented that massive 2048-pin interface at 13 gigabits per second. And by the way, that pin interface is exactly double the width of the previous generation, HBM3E. Then, on the other side, you've got Micron. They pushed volume shipments prioritizing massive capacity, delivering these huge 36GB 12-high stacks built specifically to feed AI monsters like NVIDIA's Vera Rubin platform. So whether you're focusing on maximizing the width of the data highway or maximizing the sheer capacity of the storage, both of these giants are using advanced packaging to feed these absolutely voracious AI models. But of course, this level of performance definitely does not come easily. That brings us to our final part, Section 5, Challenges, HBM4E and beyond. We're going to touch on the physical costs of this speed today, and just as a quick heads up, we'll actually cover the remaining side headings and challenges in much more depth in a longer explainer video down the road. But let's look at the immediate hurdles. Living on the absolute edge of physics has a systemic cost. According to Siemens' 2026 HBM Design Guide, engineers are fighting some massive battles. First up is severe thermal management. Remember our 3D skyscrapers? Layering 16 active silicon chips on top of each other generates incredible heat that gets trapped in those middle floors. And placing that skyscraper literally millimeters away from a red-hot GPU? Yeah, cooling that is a nightmare. Then you have signal integrity. Firing data flawlessly across a 2048-pin interface at high speeds is highly susceptible to interference. Add in the need for incredibly robust power delivery and maintaining high manufacturing yields when stacking 16 fragile layers of silicon, it's intense. Because of all this, engineers can't just verify a single chip anymore. They have to run complex physical verifications across the die, the interposer, and the entire package all at once. And despite these immense physical challenges, the evolution of this tech is absolutely relentless. HBM4 isn't even the final stop for this year. Samsung already began shipping 12-layer HBM4E samples in May of 2026. This immediate next iteration pushes transfer speeds up to an unbelievable 16 gigabits per second. The hardware industry literally has no choice but to move at this breakneck pace just to keep up with the soaring, insatiable compute demands of modern AI models.
So if you want to sound like an absolute expert the next time AI hardware comes up in conversation, keep these core concepts in your back pocket. HBM is high-bandwidth memory, brought right up close to the processor to feed AI workloads. TSVs, or through-silicon vias, are those microscopic vertical elevators making 3D memory stacking possible. CoWoS is TSMC's 2.5D advanced packaging tech, the high-speed bridge integrating the compute and the HBM on an interposer. And the big takeaway, the why behind all of this? It's because overall system performance is no longer just about having the fastest processor. It fundamentally relies on having high-density, high-bandwidth interconnects between your compute and your memory.
Which leaves us with this final, somewhat provocative thought to ponder. When we look at these engineering marvels, through silicon vias, massive 3D stacking, and CoWoS, is AI hardware really just about shrinking transistors anymore, or is the true revolution happening entirely in the packaging? I want you to really chew on that the next time you hear a headline about a new AI supercomputer being announced. Thank you so much for joining me for this explainer. If you found this in-depth breakdown of the underlying hardware techniques helpful, make sure to seek out more of our deep dives into the fascination of modern engineering. Until next time, keep learning.